Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we talk all things general chemistry related. On this quick video, I'm going to be covering what isotopes are and how they differ from other elements. Let's get started. If you recall back from a previous video, we talked about how in Dalton's law, he had stated that all elements would have the same mass if they were considered to be the same element. However, several studies later on found out that, in fact, the number of neutrons within an element could vary. So remember, all atoms of a given element will have the same number of protons. Remember, that's how we define the element. However, they do not always have the same number of neutrons. So the fact that they have different number of neutrons, well, if the mass is equal to the protons plus the neutrons, that means that the overall mass could vary. So in fact, contrary to Dalton's theory, all atoms of given elements do not have the same mass. Atoms with the same number of protons, but different number of neutrons, those are what we call isotopes. Now, the relative amount of each isotope in a naturally occurring sample of a given element is usually the same, and we know this as the natural abundance. So let's try working out atomic symbols based off of the information that's provided below. In the atomic symbol, we're going to show three parts. We'll have the symbol with its respective letters. On the bottom, we write the atomic number, which is the same thing as the protons. And on the top, we write the mass number, which is equal to the protons plus the neutrons. So here it says neon has 10 protons, 10 neutrons, and 10 electrons. So we would put the symbol Ne. On the top would be 20 based off of 10 plus 10. So 20 as the mass number. On the bottom, we would have 10 based off of the protons being equal to the atomic number. For the next one, we have, again, neon, which still has an atomic number of 10, hence why we're not changing the element that we're talking about. But now the mass number is going to be a bit different from the first example. When we add our 10 plus 11, we end up with 21 as the number of, as the mass number, excuse me. And then last but not least, once again, we're dealing with neon with 10 protons. Again, notice the atomic number is not changing. However, that mass number will now be equal to 22, which is from the 10 plus 12. Again, all these elements represent neon. However, the different variations are what we call isotopes. So we can actually calculate the atomic mass, which is listed on a periodic table, based on knowledge about the natural abundance of different isotopes. So each isotope that exists at a certain percentage, basically meaning the possibility of you running into that particular isotope, that particular element with that mass will have a certain percentage. And so we can calculate the atomic mass by taking the sum. So anytime you see the symbol, this means the sum of the fraction of the isotopes times the mass of that isotope. And so what I always teach my students is rather than thinking about it as a fraction, you would actually want to think about this as a decimal or input it as a decimal, because that'll just make the math a lot easier. Remember, if we have multiple isotopes, the total isotope should add up to 100. And so if we had something that was like 95% abundant, then that means as a decimal, we would write it as 0.95. The reason I like to stress it that way, it's just a little bit easier to type into your calculators when you think about it as a decimal point versus a fraction. And so what you would end up doing is taking information about multiple isotopes and plugging it in to this equation. Now let's imagine that we had something that had two isotopes. So to calculate the atomic mass, we would take the abundance of the first isotope as a decimal times the mass of that isotope. Okay, and so this represents isotope 1. And then we would add that to the abundance, again, written as a decimal point, of the second isotope times its mass. And this would represent isotope number 2. And you can fill this, keep going depending on the number of isotopes that you have. Now, when you're charged with this, doing this type of problem, you could always check your answer based off of, if you're solving for the atomic mass, refer to what's on the periodic table and see, does your answer align? If it doesn't, then perhaps you may have put either the abundance or the mass of a particular isotope in the wrong spot. Now, these problems could also be presented a different way where you are looking to solve for the mass or the abundance of one of the isotopes. And I'll go through an example of how we'll manipulate this formula to do that. Look at a problem here. It says copper has two naturally occurring isotopes, copper 63 with a mass of 62.9396 AMU, so AMU stands for atomic mass units, and a natural abundance of 69.17%, and copper 65 with a mass of 64.9278 AMUs and a natural abundance of 30.8%. Now for this problem, we're going to be calculating the atomic mass of copper. So let's look at what information we were provided here. See a lot of numbers here, so it's easy to get lost in what it is that we're truly solving for. So we're told that copper 63, in this case, the 63 is representing the mass number, has an atomic mass of 62.9396 and a natural abundance of 69.17%. We are also told that the second isotope, copper 65, again, 65 is the mass number, has an atomic mass of 64.9278 and a natural abundance of 30.83. And we want to calculate the atomic mass of copper. So what this means, if we think back to that slide I just showed previously, we're solving for the atomic mass. And so we should be able to check our answer against what is shown on the periodic table. So if we set it up, our atomic mass is going to be equal to the abundance written as a decimal point of the first isotope. So if it says 69.17, that would become 0.6917, move that decimal point 2 places, times its mass of 62.9396, plus the abundance of the second one, so that'd be 0.3083 written as a decimal, times its mass of 64.9278. Now, when we plug that into our calculators, for the first parentheses, we get 0.6917 times 62.9396, and we end up with 43.53532132. Again, we learned about sig figs in the last chapter, so we still got to apply them here. And so this answer, it would have 4 significant figures because of it's a multiplication problem. So I would be, in theory, stopping there, but I'm going to carry all the numbers through to the next calculation. If I look at the second parentheses, 0.3083 times 64.9278, we end up with 20.01724074. And again, we would be stopping after 4 significant figures accordingly. Now, the last step would be adding those two together. So 43.53, et cetera, plus 20.01, et cetera. Again, carry all those numbers through to the end, and then we're going to do our rounding at the end. When we do that, we end up getting 63.55256.206, and we end up getting 63.55256.206, and then we'd apply that final sig fig rule of looking at the number of decimal places. We end up being 63.55 AMUs. If you look at the periodic table, you'll notice that that does in fact check out, and so we've gone and solved this problem properly. I'll do one more example of an isotope problem, but you're going to notice this is slightly different than the previous problem. So this says bromine has an atomic mass of 79.904 AMUs, and there are 2 naturally occurring isotopes, bromine 79 and bromine 81. The mass of bromine 81 is 80.9163, and its natural abundance is 49.31%. Here we want to calculate the mass and natural abundance of bromine 79. So again, a lot of information here. It's important to break down and distill the information that we know. So it's telling us that the atomic mass is 79.904. So we know this, we know what the mass is. Our job is to figure out information about one of the isotopes. So we know that there are 2 isotopes, so that's good information to know. And we know that one of the isotopes, bromine 81, has a mass of 80.9163 and its abundance of 49.31. And our goal is to find out the mass and natural abundance of bromine 79. So there's a lot of information that we got to weave together here. The fact that we know that there are only two naturally occurring isotopes helps us to figure out the abundance of that second isotope. Remember, the abundance should add up to 100%. So if one of them is 49.31%, the abundance of the bromine 81 would be equal to 100 minus 49.31. Go ahead and plug that in your calculators. End up with 50.69 as the abundance for that particular isotope. We would start with 79.904 written on the left side, representing the atomic mass. We're going to then set that equal to and do a parentheses for the first isotope, which we know has a abundance of 49.31. We write that as a decimal. We're going to do 0.5069, and now we're going to do times X because we don't know the mass of that isotope. We're going to be solving and calculating for that particular number. So at this point, it becomes algebra. So go ahead and plug in your parentheses. So 4.4931 times, and that should be 80. We're missing the 80, times 80.9163, and that gives us 39.89982,753. Mark off where we would have stopped, plus 0.5069 X, and set that equal to 79.904. And then we're going to isolate. So now we're going to take our answer and we're going to do 79.904 minus that answer, that 39.89, carrying all those numbers through. We end up with 40.00417,247. Again, based off of significant figures, we would only have 4 that we're bringing through. Go to 0.5069x. We would then divide both sides by 0.5069 to get our final answer. In doing so, we end up with 78.92 as our final answer. I hope this video helped, and I hope you learned everything you needed to know to tackle isotopes. Come back later and be sure to check in for more videos. Make sure you like, subscribe, and comment below for additional material you may want to see. Have a great day and see you guys soon. Bye.